Hello, and welcome to our first foray into Chapter 10 in Calculus 2. So, today we're going to be talking about differential equations. This fits in well with what we've been doing because we've been focusing on integration theory. And in particular, differential equations is devoted to how to use integrals to be able to solve some stuff. So, the first thing I have to teach you is what is a differential equation? So, this is kind of a long definition. A differential equation is an equation that has a finite number of known derivatives. So like the short version of this, it would be any equation that has a derivative in it and it's not an infinite number of unknown ones. So you know how many you have and what they look like. And I'm going to write problem because occasionally you'll have more than one equation. It's not how you spell with. A finite, so not infinity, number of known derivatives. So I know what the derivatives look like is what you should be thinking. Okay. Now a solution to this is going to be any function that when you do those derivatives, you get what you have in these equations. So a solution to a differential equation is a function with those derivatives. So to just get you thinking about this, let me do a couple examples that have the solutions to them. So if you're thinking like, what is this going to look like? Well, suppose you knew that the derivative of some function was 2x. Well, you know that x squared's derivative is 2x, so that would be a solution. Now be careful because a solution, I want you to also be thinking like there's a subtle note to the English behind this is there are going to be many possible solutions, or there are possibly many, I should say. Some things only have one solution. Just when you thought it was safe to math, let's do some English. A rather than the solution, which means there could be many. Anyway, let's do some examples to help you out with this. So what we're going to have here is we're going to have a differential equation and we're going to have a solution and we're going to verify that solution works. So take a look at A. The derivative of y with respect to x is equal to 4y. This means that when I derive the function y and multiply it by 4, when I derive the function, I get the same thing as multiplying that function by 4 is how I would read this. So I've got a solution right here where k is just some constant, so k is just some unknown number. Let's go ahead and do the derivative of y with respect to x. Now I'm using Leibniz notation here. You would have also possibly done this with y prime if you're using the Newtonian notation, just to remind you what this looks like. So I'm going to derive this with respect to x. Remember, constants you can pull out, and as you do your derivative, then I'm going to do e to a function that's not just x up in the exponent, which means I'm going to have to chain rule this. So I'm going to end up with e to that function times the derivative of that function with respect to x. So the derivative of 4x with respect to x is just 4. So that's equal to 4k e to the 4x. And I'm moving the 4 out front. Oops, I meant to erase that, sorry. As I want you to notice something. I just did the derivative of y with respect to x, and I got 4 times something that's equal to y. So I'm going to think of this as, oh, well, that's really 4y, which is exactly what the differential equation said. So check, check, this appears to work. Yes, it is the solution. Now, another way you could have done this is you could have calculated the derivative separately, like calculated this side, and then calculated 4y, and then confirmed, yes, they are equal. That's another approach to that, which I'm going to do with this next one. no wait, this one I'm going to subtract them and see if I get 0. So this one says, hey, when I do the second derivative of y and subtract y, I get nothing. So I'm going to have to take this y and derive it twice. So let's go ahead and use Newtonian notation, since that's what we got here, some primage. So I'm going to derive with respect to x. So I've got k e to the x. Do you remember constants factor out? And the derivative of e to the x is e to the x. Let's go ahead and do the second derivative. Remember, constants factor out. The derivative of e to the x is e to the x. Okay, so if I do y double prime minus y, that's going to be equal to, well, y double prime we just established is k e to the x, and the original y was also k e to the x. So it appears that this is 0, so that appears to work as well. So there we go. We checked some stuff to see if they were equal. Let's talk a little bit about elementary differential equations. So, it wouldn't be a good day if we didn't have some, good stuff that shouldn't be here. So what I want to talk to you about is what's called a general solution. Woohoo! Yep. A general solution to a differential equation Fun fact, back in the day we used to call these diffie-qs. I'm pretty sure this language is still used. So if you accidentally hear somebody talking about diffie-qs, like, that's what they were talking about. It's a little abbreviation for those guys. So you know what's up. Anyway, is a function who is a solution but has constants that are unspecified. So, for example, you'll notice that in the example I just did, 10.1.1 A and B, I had K. And we don't know the value of K. So you might ask yourself, where did K come from? Well, don't worry, I will totally show you as we go through and do some stuff here. So you might end up with some constants when you try to solve some stuff. So here we go. Let's find the general solution to the differential equation. So I'm assuming that most of you know the fact that the derivative and integral are opposites of each other, that they undo each other, and I'm going to essentially use that trick to solve this one because it's easy to do. And then I'm going to talk to you a little bit about how and why that solution method works for this example specifically. So I'm doing a specific type of differential equation in this case. So what I'm going to do is I'm just going to take this and I'm going to integrate both sides. So I'm going to do the integral of dy dx with respect to dx. And I'm going to integrate the other side as well. X to the fourth minus 3x plus 2 dx. Cool. So the integral of a derivative with respect to the same integration with the same derivative, or the same differential, is just y. Because remember, the integral is asking for an antiderivative that produces that as the integrand, which means that an integral is like, hey, give me something that when I do its derivative, I get this part. Yeah? Well, y, when I derive it with respect to x, I get this part. So the integral and derivative do undo each other, and you just get the variable back. Now, what am I going to get on the other side? That's where things get a little more complicated. So luckily, this is a polynomial, which means I can just pow, pow, power rule my way through this. So I'm going to add 1 to the power and divide by it. Add 1 to the power and divide by it. Add 1 to the power and divide by it. I ain't dividing by 1. You can't make me. And then, don't forget to tip your waitress. So, ooh, there's the constant coming in. So there's like where we get a general solution. Now note you can check this solution to make sure you're right. I should have left more space for this one. I write bigger than I think I do. So if I take all this and I just prime it, so this is my check step. So I shouldn't write prime because we're using Leibniz notation. I'm going to derive it with respect to x. Derive with respect to x. Woohoo. Derivative of y with respect to x is the derivative of y with respect to x. The derivative of x to the fifth with respect to x is, oh, well, I'll multiply by 5 and then subtract 1 from the power, which will give me y to the fourth. I'll multiply by 2, divided by a half, and just get a 3, and then subtract 1 from the power to just get an x. And then here I'll just subtract 1 from the power and get a 2. And then the derivative of any constant is 0. Oh, look, it ends up, why did I put a parenthesis? Oh, look, it ends up being the original. Yay, it works. So integration, how does it relate to differential equations? It appears that if you integrate correctly, you can solve differential equations by integration. Now, looking at this next one, you might think, oh God, there's too many dy dx's. How is she going to do this? Well, let me show you. Actually, I need to take this and make it look like the one I had above. So I need to make it look more like this one where I've got dy dx by itself. So what I'm going to do first is I'm actually going to add x dy dx. Oh, I meant to put this one in Leibniz notation so you could see one with y primes. That's my bad. So that'll cancel with that. And over here I'll get dy dx. So the derivative of y with respect to x plus x times the derivative of y with respect to x equals to, oh, I'll just have a 3. And then I'll factor out dy dx. Come on, that's supposed to be a y. I hope you trust me. So I'll be left over with 1 plus x equals 3. And then I like to change colors when I do a second action in the same line. Because I'm just trying to get dy dx by itself. So now I'm going to divide by x plus 1. Or sorry, 1 plus x. Those are the same thing. So in the end, I get dy dx is equal to 3 over 1 plus x. And now I'm going to integrate this with respect to x. So again, I like to change colors when I am doing two actions in the same line. So on the, well, I'll do the left hand side for you guys. That's why. That's the easy one. On the right hand side, I'm going to have to do some u substitution. I'm going to use w though, because you know how I feel about u and all that stuff. So I'm going to use 1 plus x. Then dw will be the derivative of this, which is just 0, and dx. So if I update this integral is, oh, I'll move the 3 out front. 1 over w dw. So I'll get 3 natural log of w plus c. There's a c coming in again. Still equal to y. 3 natural log of what was w? 1 plus x plus c. Hopefully you're getting an idea for the strategy behind this and how you might solve it. But in case you weren't, let's name that strategy and talk about how it's done. So this is something called separable differential equations. So this is when I have a differential equation, that looks like, oh, the derivative of y with respect to x is equal to some function of x and y. So I'm just going to call it h. Yeah? I don't know what h is, doesn't matter. This is just kind of like a placeholder. We call it separable if you can write it like the following. Oops, I missed my R in written. It can be witten. I think that's a word. It might be a word. Probably not a word. I'm going to go look that up later. As, and this is the kicker. This is very important. I don't know. Let's use f and g. F of x. Actually, usually I put x on the other side, so I'll erase this. F of y dy equals g of x dx. Now, this is very important that you recognize what's happening over here. This function is only of y and this function is only of x. So it's basically saying, hey, if I can put all the x's on one side and all the y's on the other, only y stuff, only x stuff, then you're good to go. And then you can just integrate both sides to get a solution. And that's the important part. So separation of variables or separable differential equations is super important. Put like hearts and stars all over this one because it's the easiest way to solve. Now, I actually did separation of variables in 10.1.3, the example we have above this in blue, purple, and orange. I directly did it. I just separated everything apart and we were good to go. And it made it so I could integrate. Let's see some more examples of that because that's the goal of today's section, is to do separation of variables. So here we go. So I got dy dx is equal to x over y. So what I'm going to do is I'm going to take both sides and multiply by y to get y to the other side. So I'll get y dy is equal to x dx. Now I've moved my differential overs to make this easy to integrate. I'm going to integrate both sides. Oops. Again, I usually try to write my separate steps separately, but I just failed at that right there. My integration step is actually separate from my differential step, or sorry, my separation step, but you know, then we integrate. Woohoo! So the integral on the right hand side, I'm going to integrate y with respect to y, so I'm going to add 1 to the power and divide by it, equal to, let's add 1 to the power and divide by it, because I'm integrating with respect to x this time, and then let's throw in our plus c. Now, little note here. Technically, from integrating both of these, like, you should get a constant on both sides, but you could just subtract the constant from the y side over the x side, and you end up with combining your constants into a new constant. Who cares? Just write one. And then usually what we do, we solve for y. Now, that's not actually easy to do in all of these, so just be aware of that. In this case, it's not too bad. And it actually makes stuff looks a little bit nicer, I think. And it helps you easier see that this is actually a circle. So I'm going to take and multiply by 2 to get y by itself. Remember, multiply everybody by 2. So here we have some cancel, here we have some cancel. A constant times 2 is just going to be that constant. It is just a constant, a new constant, and I don't care. I'm just going to call it c. And then to get rid of the square, I'm going to take the square root. Don't forget, anytime you take a root, you get 2 solutions. So here I'm going to get y is plus or minus the square root of x squared plus c. Now, alternatively, you could have rewritten this as like, well, I have y squared minus x squared equals c. And then you're like, oh, that's a hyperbola. Because I remember those from when we talked about them back in graphing, and it's fine. Usually we solve for y. So most of the time when you're writing your answers, they will look like this. Good times. Let's do another one. Hopefully you recognize that this one looks very similar to the one we just did, but wait, there's more. Let's solve some things. Okay, so I gotta move y over to make it with the y side. I generally always put y on the same side and then just leave my x's on the other side. Wonk. So here I get 1 over y, dy dx. Oh no, wait, I'm gonna move my dx over for my separable version of this. 50 x dx, and now we're going to integrate. Let's do orange this time. Orange. Integrate. Integrate. Notice where I put the symbol because I can just factor the constant out. Oh, there's no point in doing that with this one. So add 1 to the power and then divide by 2, so I'll get 25 plus c. I like to put it on the x side. Ooh, what's the integral of 1 over something? Well, think about whose derivative is 1 over something. It's the natural log. Uh-oh. This is a fun time. I like the natural log ones. They pop up actually a lot in nature when it comes to how things are related with direct variation. So this is actually a really common solution for you guys to see. So I need to get y by itself, which means I need to exponentiate. Hopefully you know the inverse of the natural log is the exponential. So e to the 25x squared plus c, and these two will undo each other, so I'll just get y. And then I'm going to do some funky moves on this side. Hopefully you remember that adding inside of exponents is the same as multiplying. That 5 looks horrible. So this is e to the c. So then usually what we'll do is on the side here we'll say let a be the constant equal to e to the c. And we'll rewrite this as y equals, we'll replace that with a, e to the 25x squared. And hopefully you recognize that this looks a little bit like the PERT equations, or P equals e to the RT. So looks PERTy, because I think I'm funny. What'd you do in math class today? We learned about PERTy equations. Ooh, that sounds crazy. Maybe don't tell people that. Should be a fun time. Yep. I like this next one. Let's get this party started. Get this PERTy started. Nope, done. Not going to do that again. Okay, cool. It appears my equation on this side is all y's. Fun times. So I'm just going to multiply by its reciprocal to get it over to the other side. Or, as you might say, I'm going to divide by it. So over here I'm going to get 3y squared plus 2. Oh boy, 2's are just challenging with this digital pen. Just challenging. Y cubed plus 2y plus 1 dy equals 2. Well, I divided this by itself. When you divide something by itself, you get 1. And then let's go ahead and integrate. Alright, so the left-hand side is going to be fun. You guys do the right-hand side. I happen to have noticed that it appears that I have a cube in the denominator whose derivative appears in the numerator. So this is going to be w equals y cubed plus 2y plus 1 dw is 3y squared plus 2 dy. So when we update this, on the left-hand side, we just have the integral of 1 over w dw equals, well, let's go ahead and do this integral because we can. The integral of 1 is x plus c. And then hopefully you recognize the integral on the left-hand side is 1 over stuff, so I'm just going to get the natural log of w equals x plus c. So I'm going to rewrite this all using the exponential. W equals e to the x, and it should be plus c, so I'm just going to throw that a out there. That trick is going to happen 8 million times, just so you know. And then you remind yourself what w is, and then you realize I am not going to be able to solve for y, hopefully, because it's just not going to be possible. It just isn't. If you wanted to at this point, you could do some factoring to try to simplify this, and then some dividing to try to make this look nicer. I mean, I did try this on the side of my notes because these both have a, this is an irreducible, it turns into a factor of x times, or sorry, y times 1 times an irreducible quadratic, so at that point, like, you can't go any further. We're done. So maybe sad times can't really solve for y. But this might still be usable if you're trying to solve something complex. You have a equivalent ratio, so you could just do like, hey, I'll figure out where these are equal, and then that would work. But I have a feeling it's a complex answer. All right. Here we go. Last one. And then we're going to do some initial value problems. All right. Do I like this one? I don't remember. It's fine. We're going to divide by y to the 5th. Always moving that y over. So on this side, I'm going to have y to the negative 5 dy equal to, e to the 2x dx. Let's integrate this up. I really like the orange today. It's feeling bright and sunny. Kind of nice. Hopefully it's bright and sunny where you are, wherever you are, and you're having a good day. Okay, add 1 to the power and divide by it. Let's do this. Y to the negative 4, negative 4. Why do I say 4 weird? I don't like it. Integral of e to the function. Remember, it's e to the 2x, and then it's the opposite of deriving. So deriving you would have gotten times at 2x. Here, we're going to end up with dividing by 2 plus c. Okay, let's do some solving. I want to get rid of that negative 4. Yeah? Red's a bad choice. Purple. So yeah, I think I'm going to first up multiply everybody by negative 4. So on this side, I'll end up with just y. Let's put 1 over 4. There we go. I like that better. Equals, so if I multiply through by negative 4, I'll get negative 2e to the 2x. And again, constant, it's just going to be some new constant. I don't really care. We're just going to call it c. Still need to solve for y, so I'm going to invert everybody. Invert. So then I get y to the 4th equal to 1 over negative 2e to the 2x plus c. I'm going to do a very similar move to this when I do the stuff with the logistic regression in the next section. So just, watch out for this move. If you have 1 over stuff, you can just flip everybody and then that's in the numerator and that's in the denominator and things work. And then I got to take the fourth root. Remember, with even roots, you always get a plus and a minus version. The fourth root of 1 is just 1, so I'm going to just leave that 1 in the numerator. And then leave the denominator like this. This is not pretty. Sorry. If I only ever showed you pretty stuff, I wouldn't be doing my job. That's for darn sure. Oh, I wish that was nicer. Let's end my root. That's where we go. Okay, so what are we going to do next? You might be asking yourself, well, are there going to be circumstances where I'll know what these constants are? And the answer is yes. When you are dealing with initial value problems, you have an additional piece of information about your differential that lets you know what value c is. Or you can use it, rather, to solve for c. Are you ready? I hope so. Feel like a cheerleader. Ready? Okay. I don't know what's wrong with me. Move the y over by dividing by 1 over y plus 1. I'm not even writing the algebra now. That's not good. 1 over x dx. I almost forgot that x was in the denominator and tried to move it out. That would have made this super wrong. Eraser. Eraser. It's been trying to do the lasso. I don't know why. I'm going to use this later to figure out what my constant is. This is going to be some log fun. So let's integrate. Whoomp. Whoomp. The integral of 1 over the stuff is going to be the natural log of the stuff. Now I don't need to do substitution with this one because, well, the derivative of y plus 1 is just going to be dy, so I can get away with cheating on that one. But if you need to see that step, you should totally do that. Okay, so to do this, I'm going to have to exponentiate both sides. So I'll get e to the natural log of y plus 1, close parenthesis, equals to e to the natural log of x plus c. Be careful, a common mistake with this is for people to pull the c down. Remember, you're exponentiating both sides to do this. This will cancel and you'll get y plus 1. On this side, I'm going to have to do some rewriting because I have this plus in the way of me doing my cancellation. So remember, addition in the exponent is the same as multiplying with the same base. Let me do a quick little side note on that. This is going, let's just put it right here. You may remember a long time ago, when you have things that have the same base, like x to the fourth and x cubed, you can add their exponents. 4 plus 3 makes 7. So that's what I'm using. I'm saying, oh, if I have the addition, I can rewrite it like this. I'm going the other way. Usually we use this idea, I should have made this box bigger, the other direction. Come on. Okay, that's it. I'm just flat out clicking eraser. I want to write this a little differently. So if you remember your exponent rules, come on, there we go. That's what's happening. Usually when we teach you guys this, we write it as like, oh, I have base to the power n times base to the power m. And then I add my two bases together, m plus n. So now I'm starting with, oh, I have them added. I'll separate them because now I can do this. E to the natural log of stuff is just the stuff. And then e to the c, you know what I'm going to do. I'm going to call that a. Y plus 1 equals a. A times just x. Ooh, that's kind of fun. And then I'll subtract 1. So I'm going to go all the way over here with this. Y plus 1 equals ax minus 1 minus 1. Y equals ax plus 1. Or sorry, minus 1. Oops, almost did that wrong. Cool. And then I know at y of 1 I get 2. So y is 2 when x is 1. Minus 1. So I'll just add 2. Cool. So I'm using this value right here. Y equals 2 when x is 1. Itchy, itchy. So, oh, you know what's awesome? When you add the same things to both sides so that you're actually correct. Yonk. 3. Hey, what's a? It's 3. Cool. So I can now write my final solution as y is actually 3, not a. X minus 1. It's actually a line. That's kind of fun. So this line in particular, when it starts at the point, or has the point 1, 2 on the line, has the following slope function. Yeah? Kind of trippy, right? Let's do another one. I think this one's harder. Oh yeah, this one's much harder. Let's get down with our bad selves. I know that one seemed like a lot of work, but I was a little worried about some stuff. Okay, oh, I just got to move the y over. So y to the negative 2 dy equals x over x squared plus 1 dx, and we'll integrate both sides. The left-hand side is going to be easy. Add 1 to the power and divide by it equals, here I'm going to need a u substitution. So let's change it up. W is x squared, that's a horrible x, plus 1. And then, so dw will be 2x dx, and I'll divide by 2. So here I'll end up with a 1/2 integral of 1 over w dw. So let's go ahead and rewrite this a little bit. So this is negative 1 over y equals 1/2 the natural log of w plus c. I'll replace the w in a minute. Let's solve for y. So the first thing I'm going to do to solve for y is I'm going to change everybody's signs. And again, I don't care about c. I'm not going to change its sign. So plus, minus. I mean, if you want to put a minus there, you can. If it's really going to bug you, fine, I'll put it. So you get 1 over y is negative 1/2 the natural log of whatever w is. We'll get back to that, minus c. And then we're going to go ahead and invert everything. Because that'll get y up top. So y is 1 over negative 1/2 the natural log of, okay, let's remind ourselves what w is, x squared plus 1 minus c. There you go, minus c. You really don't have to do minus c, you can do plus c. Alrighty, now we need to put in our point. So y equals negative 1 when x is 0, so this is really the point 0 minus 1. Let's put some values in. So negative 1 equals y, 1 over negative 1/2 natural log of something minus c. So notice everything's going to be gone except for c, so I'm going to be able to solve for c, which is awesome. So when x is 0, I'll square 0 and get 0, plus 1 is 1. Hopefully you remember that the natural log of 1 is 0, so this is just going to go away. So I get negative 1 equals 1 over negative c. Oh, okay, so let's invert. So I'll have negative 1 over, or sorry, 1 over negative 1, so you can see me, you know, if you don't like inverting, which I do a lot when it comes to these, okay, come on, erase. You can do cross multiplication with this one, which is kind of fun. Negative c times negative 1 will just be c, and then 1 times 1 is 1. Done. C is 1. Let's write our final answer with c in it. Natural log minus 1. Now, fun fact, back here I changed the sign to be negative c. If you go through and do this with this being a plus c, then when you get to this step, you don't have negative c, you have positive c, and c comes out as negative 1, so then you have plus negative 1, which is minus 1. They come out the same either way, is what I want you to see. So if you're worried about sign changes, as long as you keep it consistent, you won't have to worry about it. It'll be correct either way, which is the nice part about this. Let's do an application problem. Now you might not like this one, but it's important that we do some. Here we go. So your monthly sales are falling at an instantaneous rate of 5% per month. If you're currently selling 1,000 quarts per month, find the differential equation that describes your change in sales. It's going to describe how you're changing. Solve the differential equation to predict your monthly sales. All right, let's set up our DiffyQ. So we know the rate at which we're falling is 5% of the current rate per month. So my change in sales over time is I'm going down by 5% of my current value because I'm describing the change. Your instincts might be to start with, oh, well, I'm doing 95% of the original. That works too. It'll come out the same. I like including the 5% decrease. So I'm going to have, I'm using S for sales just so you have like a little thing, and T for time. And since we're doing this in months, I'm going to call it monthly. Woohoo. Okay. Whew. All right. You currently sell 1,000 quarts per month, which means that at whatever time we're starting at, which I'm just going to call it time 0, we have 1,000. So this is my initial value. So we'll call this current month. It'd be nice if they gave you like third month in the quarter, because then it would be S of 3 is 1,000. So this is our differential equation, our diff EQ. Let's solve it. All right, so S is playing the part of my Y variable, so I'm gonna have to divide by S to get it to the other side to be able to separate this. So I'm gonna go ds 1 over S is equal to negative 0.05 dt. And then I'm going to integrate both sides. And I got to be careful with my s's because they kind of look like my 5's. Cool. So integrating the left-hand side, 1 over the stuff, we've already seen lots of natural log action happening here. So one of the reasons it's called the natural log is because it comes up a lot in nature. Cool. On this side, I'm going to get negative 0.05 t plus my constant. Cool. Let's exponentiate both sides, or rewrite this as an exponential. So on this side, I'm just going to end up with s, and on this side, I'm going to e.05 t plus c. I'm going to change this with the whole a thing that we've been doing this whole time, and you'll see why that helps when it comes to using the initial value. So let a be e to the c. So then now my s equation is a e to the negative 0.05 t. Now let's use that information we have about 1,000. Let me scroll this up a little bit just because I'm running a little bit out of space. It's still not thinking. It can't tell the difference between the pen and my mouse sometimes, and that's happening right now. Yes, I'm good. Okay, so at time 0, I should have 1,000, so S is 1,000. A e to the negative 0.05. 0. Well, that's going to be 0. E to the 0 is 1. So on this side, I'm just going to a times 1. So what's a? It's 1,000. So S is 1,000 e to the negative 0.05 t. There we go. That's my solution. So there's my solution, or my equation that does this deduction. There we go. That was hard to get out. Whew. Let's do something with elasticity of demand. Now, hopefully you know enough about this from econ to where this will be a little more comfortable for you than it is for me, just so you know. But this is a nice application of how you can use calculus to do some calculating for, well, elasticity of demand. Anyway, in case you didn't know, the elasticity of demand is defined by the opposite of the price per quantity times the change in price, in quantity per price, which is what I have right here, the equation for elasticity of demand. Anyway, if a product's elasticity of demand is modeled by the following equation, so I know E, find the equation for Q as a function of P if it is known that when the price is set at $20 per unit, the demand will be $20, or 20 units. So we have this set point, and we have something that describes the elasticity. We're going to use the demand equation to figure out what this is going to look like. So since I know the value of E, I'm going to replace it in this equation with what it's equal to. So 0.05 P minus 1.5 equals minus P over Q dq dp. So what I want to do at this stage is, well, I want to separate it. I want to get all my P's on the other side and then leave all my Q's on this side. And I'm sorry my Q's look weird. Maybe I'll just do my Q's as capitals, because then you won't confuse them with your P's. I like that better. DQ. Oh, that makes me want Dairy Queen. Okay, so now that we've got this set up, let's go ahead and do some solving. So again, I want to move the P's to the other side so I can separate this. So I'm going to multiply this side by 1 over P. I'm going to leave the negative on this side because it doesn't matter where you put it. And then same thing over here. Multiplying by 1 over P is essentially dividing by P. So for this first term, I'm going to end up with 0.05. For the second term, I'm going to get 1.5 with P on the bottom. P. And then let's just go ahead and separate this. So dq on this side, dp on this side, integrate both sides. One of the common mistakes I'll see with this is people will integrate only this term because it has the dp next to it. Remember, this is indicating that the entire thing is a part of my differential, not just the last term. You integrate both sides, not parts. So be careful with that. Sides, not parts. Oh, and before I go any further, make sure we make note of our information here. When P is 20, Q is 20. And usually you can get that from like a market survey. Oh, when I had this price, how many did I sell? Which is kind of nice. Let's integrate. So add 1 to the power and divide by it. Here I'm going to get 0.05 p minus, I can factor out the negative 1.5, and then I have 1 over p, whose integral is going to be the natural log of p, equals, oh boy, which side do I want to put c on? I don't know. Negative natural log of q. Which side should I put p on? It's going to be easier to solve for q, so I think I'm going to put it over here. That was an elective choice. Totally choice oriented. Nothing to do with anything else. Okay, so then to solve for q, we're going to have to do some exponentially. Ing? Yeah, okay. So here you're going to get e to the c plus 0.05 p minus 1.5, the natural log of p, equals, oh man, the negative's in the way, e to the negative natural log of q. Uh-oh. I'm going to have to use some algebraing to do this. I should have moved that negative over because that would have made this easier. That's okay though, we can still do this. It's not a big deal. If you remember your rules for natural logs, if you have a constant out front, you can just, I shouldn't have used p because that's already in our equation. Eraser. Eraser. Nope, not going to do it for me, are you? There you go. And that's the same as I can move it inside. So I'm going to rewrite this as e to the natural log of q to the negative 1 power. So I can undo these two. This is something I should have left more space for because I'm at the bottom. So over here, I get q to the negative 1, which hopefully you know is 1 over q. Oh boy, this is not pretty. Why did I do this? Okay, I know why I did this one. It's because it's related to what you all do. Let's invert. So q is equal to 1 over that disaster. E to the c I can just redo as an a. So a e to the 0.05 p minus 1.5 the natural log of p. Okay, what you should do next is put in 2020 and solve for a, which isn't easy to do. Would it have been easier to do up here, I wonder? It would have been, yeah, because then you'd have 1.5 natural logs of 20 and you'd just subtract one of them and you'd end up with half of one. Oh my god, that's what I should have done. Okay, I'm an idiot. I should have solved for c back here and then did this stuff to solve for q. Why did I do that to myself? Oh, regret. Oh well. Now that I've like on a bad note, let's end this. So what you have learned from today? How do I solve differential equations? I find things that when I do their derivative, I get the differential equation. How are we majorly going to do that? Well, we're actually going to learn lots of ways to do it, but the first way that we are going to use is separation of variables, which is collect all your p's to one side, all your q's to one side, integrate each side, go ahead and do some solve in action. And sometimes, if you're given an initial value, you won't have constants. Good times. Hope you've enjoyed this episode of, I don't know, whatever I'm calling calculus. I always want to say calculus fun time, but, I have no idea. Peace out.